again, we have 2x cubed y, and now we really are doing a Lagrange multipliers problem. We have this constraint x squared plus y squared equals 4. So Lagrange multiplier says we want to see when does the gradient of f equal a multiple of the gradient of the constraint equation. So if we write g of xy equals x squared plus y squared, we want to see when we can find x, y, and lambda so that this is true and so that this is true. I've already computed the gradient of f in some sense. I've already computed both first partial derivatives. The first one was 6x squared y, if you recall, and the partial with respect to y was 2x cubed. And we're seeing when this is a multiple of the gradient of g. The gradient of g, well, the first partial derivative with respect to x will be 2x, and then the partial with respect to y will be 2y. So the equations that we're solving are 6x squared y equals lambda times 2x, and 2x cubed equals lambda times 2y. That's just by setting each component equal to each other. And so we have these two equations and also the constraint equation to satisfy. So this is 3 equations and 3 variables. You would normally expect that this should have a finite number of solutions. Let's do a little simplifying. As I've already said, well, first of all, I can cancel some 2's. I can cancel a 2 here and make this a 3. And now, initially, one strategy with Lagrange multipliers is to eliminate lambda and then just get 2 equations involving x and y. And now I know that x, we can assume that x is not 0 by this argument from before. I'm looking for maxes and mins, and even if Lagrange multipliers told me that there are some with x equals 0, I would know that that's not the maximum or minimum because there are points that you can plug in here that make this negative and points that make it positive. So that allows me to cancel some x's. I can divide by them because I know that it doesn't make sense for them to be 0 in this problem. So this equation, I can divide out the x and get 3xy equals lambda. So that's by canceling this x and canceling 1x over here. Let me write this separately. So the equation I have now is 3xy equals lambda and x cubed equals lambda times y. And now just inserting this expression for lambda into here, I get x cubed equals 3xy times y. I'll go ahead and cancel x again because it's not 0. So if I cancel an x here and an x here, I get x squared equals 3y squared. Now going back to the original constraint equation, I have this, and now it's nicely written here. We looked out that I can replace x squared with 3y squared. So really I have 4y squared equals 4. If you solve this, you get that y has to be either 1 or negative 1. And going back to here, whenever y is 1 or negative 1, x squared is 3. So you get that x is plus or minus square root of 3. And notice we get all possible combinations. So when y is 1, both square root of 3 and negative square root of 3 work. And when y is negative 1, both combinations work. So this says the points to check are, let's see, square root of 3, 1, square root of 3 minus 1, negative square root of 3, 1, and negative square root of 3, negative 1. And if you plug these into the function, the original function was this. If you plug these points in here, you'll find that this one corresponds to a value of 6 times the square root of 3. So does this one. And these two correspond to values of negative 6 square root of 3. So the maximum value has to occur at the points in this list, and we found the biggest value in the list is 6 times the square root of 3, and the minimum value is negative 6 square root of 3. This occurs at square root of 3, 1, and negative square root of 3, negative 1. And this occurs at negative square root of 3, 1, and square root of 3, comma, negative 1. And that's it.